I would like to take a moment to extend special thanks to Offshore Europe, the American Institute of Mining, Metallurgical, and Petroleum Engineers, and to our employers and Mine SLB for funding and supporting SPE's Distinguished Lecturer Series. And before we get started, I wanted to take a moment to also thank your section, Central Ukraine Section, for your interest in the topic and for extending the invitation to me. I'm very excited to join today and to be able to share this presentation, as you've already introduced it, Coiled Tubing, the Journey Toward Automation and Beyond. So today's presentation at its core is about how we ingest coiled tubing data and how this has taken us through a journey toward automation. So first, I want to provide a primer for the uninitiated about why we even bother with coiled tubing as a well intervention service line. I will draw your attention to the data journey, which spans nearly 3 decades and which I'm presenting through the lens of 3 stages, which are observe, act, and automate. I'll illustrate that evolution through some examples, and I'll make a prediction about what's going to happen in that last mile of the journey. And then at the end, we can have some Q&A. So first things first, why bother with coiled tubing? As wells mature, as I'm sure we all know on this call, they lose their capability to produce efficiently. And this is typically due to a combination of reservoir depletion and damage mechanisms in the wellbore. Now, coiled tubing has been used for over 70 years to maintain wells and restore production, namely because coiled tubing is able to convey tools on the downhole end and convey fluids to the downhole end. However, as the wells become increasingly complex, which they are, so is the task of squeezing every last drop and prolonging the life of the wells. And this is why the journey toward this digital world is so important. So with that said, let's talk about what's required to run coil. And I mentioned this is for the uninitiated, so it's some basic principles. First, at the heart of the operation, you have your coiled tubing pipe, which is this long continuous tube, typically in the range of 1.5 to 3.5 inches outer diameter, and can be, 30,000 feet or longer. You have your injector head, which is the muscle of the operation. It's responsible for gripping that coiled tubing and pushing it into the well and out of the well. You traditionally have an operator who sits in a cabin and who's responsible to ensure that the pipe is safely and reliably tripped into the well and out of the well. And then you've got your downhole tools, which could be as simple as a nozzle or as sophisticated as a powered tool that sends data in real time to the surface, or that you can interact with that tool from the surface with commands to the downhole tool. So with the benefits of pumping through this coiled tubing and conveying these downhole tools, we start to see many applications which include stimulations, nitrogen lifting, fishing, logging, milling, and you can see the word cloud that I put there. And even if you're not a coiled tuber, I would imagine that in your line of work, being in the oil and gas industry, you're going to intersect with this kind of work, right? You're familiar with some of these terms. But given its versatility, or I should say, and given its versatility, coiled tubing provides coiled tubing specific variants for each of these. So even if we're not all tubers on this call, I hope you will see how this scope of work intersects with your line of work. So now that I've talked a little bit about the mechanics of the operation, I want to talk about the data. At the surface, we have circulating pressure, which is the pressure generated by the fluid that we are pumping inside of the coiled tubing flow path. We have a mechanical counter. Typically, it sits at the injector head, and this will measure for us how much coiled tubing we've pushed into the well or pulled out of it. We have a load cell. This is usually pancaked in the injector head, and it will give us the coiled tubing weight. And then we have wellhead pressure. It's important to note that for about 80% of the operations worldwide is very back of the envelope number, right? But on a, very generally speaking, 80% of the operations, this is practically all the operational data that we have, the surface data. And then in the other 20% of the operations, we have access to real-time telemetry, which is enabled by some kind of cable that we inject inside of that coiled tubing. Now, depending on the downhole tools that we run on the downhole end of that coiled tubing pipe, we can monitor an assortment in several combinations of downhole measurements and therefore downhole conditions. You can see some common examples here with pressure, temperature, casing collar locator, CCL, gamma ray, so on and so forth. The rest of this presentation focuses on operations where we have access to these real-time downhole data. And these prove essential to the journey toward automation. Now, Rome wasn't built in a day, and the data journey is no different. So let me take you through this journey. At the turn of the century, we start to see that operators and service lines are interested in improving depth control. And given the technical, let me call it the relative technical simplicity of a casing collar locator or CCL sensor, it's not a surprise that this is one of the earliest real-time modules available for correlating depth. So once the community grew more comfortable with transmitting downhole data to the surface in real time, they started introducing more sophisticated technologies such as pressure sensors, temperature sensors, oftentimes those travel together, gamma ray, and later we see tension and compression. You'll see in later slides, tension is sometimes referred to as thrust, but it's the axial force along with compression, torque, and then flow metering. These data enabled important step changes to coiled tubing operations. And just to give you an example, CCL and gamma ray together enabled very accurate depth control, which opened the doors to depth critical operations. Downhole pressure enabled identification of fluid levels and the inference of the changes in fluids or fluid weights during the intervention. So before we had access to these data in real time, we basically had to guess the fluid levels based on an old log or simply assumptions. Depth control, fluid recognition, and logging capabilities brought our conventional work, such as stimulations, cleanouts, and nitrogen lifting, to an entirely new level. The intervention could now more accurately control the tool conveyance and the fluid delivery. Plus, now designs could be fine-tuned on the fly to reflect real downhole conditions. And so this marks the early days of optimizing a coiled tubing intervention based on real-time data. The important takeaway of this first stage that we're looking at here is that we're mostly observing. Okay, we're observing the downhole environment, we're observing that through that downhole data, but we're not yet controlling the downhole tool so much, and we're still kind of far from controlling that downhole environment. In the second stage, we enable on-demand activation of downhole tools and services. Now, this could be through means of pressure pulses that are sent from the surface and interpreted by the downhole tool, or through more sophisticated means through electrical or optical telemetries. The on-demand activation enabled applications such as selective underbalance perforation, anchoring of plugs, and operating electrically driven downhole tools. In this stage, we continue to improve our ability to extract useful insights from the data, and that's a constant throughout the journey, right? So it's not like observation was the first stage and then we never worried about it again. We continue to climb that learning curve and get better at it. It's also important to note that to this day, we continue to see new tools being developed that can be activated from the surface. So that's another constant that is being developed throughout the journey. It just so happens that in this decade, at this stage, more or less circa 2010s, is when we start to see much more development in that area of on-demand activation. Now, when coupled together, observation and on-demand activation close feedback loops, which are critical building blocks of automation. And this is the leap that the journey takes in the third stage. The age of automation for cold tubing operations is still young, so we're only starting to hear about these advancements and read about these case studies. Now, a first step that we're witnessing is software that aggregates a lot of different data, analyzes it in real time, and makes intelligent recommendations to the coiled tubing operator. In other words, we're starting to see execution advisors. Another milestone of this stage is the automation of coiled tubing conveyance, which becomes possible when the execution advisor is integrated into the is integrated and interfaced into the coiled tubing asset, such that it can take actions on behalf of the operator, the coiled tubing operator, that is. And that's the path that we're walking today. So to recap, we started by observing the downhole conditions, then we learned to act on demand, and today we're learning to successfully automate aspects of our operation. So what happens when we reach the finish line? I expect that we will have the most technically challenging and complex level of automation, which is coiled tubing autonomy, which means the orchestration between all the systems, including conveyance, the fluid pumping, and the service delivered by the downhole tools. And it also means adapting to deviations in real time. So you have an initial plan to get from A to Z, and then there are things that happen during the operation where those anticipated conditions aren't met, you deviate from them, and you react to that automatically. And ultimately, what happens in coiled tubing intervention autonomy is that we are able to stand back and supervise if we'd like, but the intervention is mostly self-driven. The journey has changed the way that coiled tubing interventions are conceived and executed, with increasing sophistication of workflows of what we can achieve even in just one single run. So I'm going to show you that evolution with a sampling of case studies, but I want you to take into account that this is just a representative sampling. And for each of these capabilities that I'm going to showcase, there are many examples worldwide and many that you'll find in the published literature. This first example cites the use of downhole data that nowadays is quite ubiquitous and common in any coiled tubing intervention where you have access to CCL and or gamma ray. But back when acquiring real-time downhole data was still in its infancy, this is one of the first significant step changes that the operation took, which was accurately controlling downhole depth based on real-time correlations, not memory correlations. So in this example, we see a schematic of the casing all the way to the left. You see a baseline log in the middle, and you have an uncorrelated log on the right. And the baseline and uncorrelated depth logs both include gamma ray and CCL measurements. Now, the baseline log is typically provided by the operator and sourced from a previous open hole or production log. And then the uncorrelated log is produced in real time by the coiled tubing intervention. And you see that there's an offset. So during that operation, you do a couple of passes, you figure out what your log is before applying an offset, you calculate that offset, you apply it, and then you perform another log in the interval of interest to confirm that you are actually on depth. And then the outcome is that the downhole tool is much more accurately placed relative to the completion into the reservoir. And the same goes for the delivery of the fluids when you pump them. And this opened the doors to depth critical operations, as I mentioned before, and some common examples are perforation and plug setting and milling. But even when it's not deemed critical, depth control has become a staple of most workflows where we have access to downhole telemetry. In the following examples, downhole pressure and tension were used to recognize fluid levels and interfaces. Now, in the first example, this time log measures downhole pressure and buoyance as the coiled tubing is run in the hole for the first time. Now, note that buoyance really is the tension measurement without the pressure compensation. That's really what it is. It's the floatability of that tool as you're running downhole and it sees a higher pressure. We can visually identify the well's fluid level based on the gradient change of each measurement, which are the dotted lines. So here you have the downhole pressure, and then it starts coming up at this kickoff point. But if we calculate the derivative, this is the gradient change. That's, you can see the step change here. The same goes for the buoyance, where you have basically a flat, let's call it a flat segment, and then some kickoff point, and then the buoyance changes. And if we take the derivative, that's that gradient change. So here you can see very clearly where you have the interface between gas and the top of fluid. In the second example, the depth log measures the downhole pressure of the coiled tubing as the coiled tubing pulls out of the hole. Now, again, you can see here the gradient in gray, and you can see how it changes as it passes through interfaces of fluids and also fluid and gas. In my opinion, this example is a little bit more interesting because we can not only see the gas brine interface, but also the interface between the brine and the produced fluid beneath it. In this case, the gradient with respect to the TVD provides the operator with an indication of the fluid weights. Now, because you are pulling out of hole and these are dynamic conditions, I wouldn't call this per se fluid weight, but it's a pseudo gradient of sorts that you can calculate when you take that evolution of the pressure as a function of true vertical distance, TVD. So this information was used in this case study to validate or for the operator to validate that brine cushion that they had here in the middle, because they could see that it was very close, the fluid gradient or the pseudo gradient was very close to what they expected to have, which was the brine cushion. So understanding not just the fluid level, but the distribution of your column of fluids, and by extension also the possibility of estimating these pseudo gradients, is incredibly useful in an operation where you seek to optimize what is pumped, when it is being pumped, and how much of it should be pumped. And a simple example of this optimization problem is when you pump nitrogen for a nitrogen lift. So where the circulating depth will be prescribed is very largely dictated by fluid levels and the column that you have in the wellbore. With anchoring of mechanical plugs and inflatable packers, we're now going to transition to the stage of leveraging on-demand activation and acting on the downhole tools and environment. Now, in this case study, the operator wanted to abandon a lower interval due to a very high water cut. And to achieve this, they ran a hydraulically anchored packer, or plug rather, on the bottom of the coiled tubing, and they were going to set that as a primary barrier. So they start the run, they correlate, and then they place the mechanical plug at the target depth, and then they start filling the coiled tubing with fluid to anchor that hydraulically set plug. So this is what you're seeing is the parameters as they're pumping inside of the coiled tubing flow path. Now, the first indication of anchoring occurs at approximately 500 PSI differential pressure, which is when the setting tool stroke initiates. And we also see this stroke validated in downhole tension. By design, a weak point in the hydraulic setting tool was expected to yield at about 1700 PSI. And as evidenced by the differential pressure, a downhole pressure spike reached 1787, very close, before it equalized. And this is immediately followed by a compressive moment as measured by downhole tension, which is the final setting stroke of the plug. So these downhole data and the information that they provide the operation are critical, especially when we're talking about plugs, where we must address the risk of premature setting, of coiled tubing becoming stuck, and of a primary barrier that you definitely don't want to fail. Now let's move on to perforation. In this example of underbalance perforating, we start to see how observation and action come together to deliver a much more sophisticated workflow, all in one single run. The intervention that you're seeing in the slide comprises 8 distinct stages. So from left to right, the coiled tubing runs in the hole and identifies the fluid level. It then fills the annulus, correlates and places the guns at depth. Then they send commands through the coiled tubing annulus to activate the perforating head, which has a programmable delay. With the firing head activated and the delay counting down to detonation, they pump nitrogen through the coiled tubing path to displace the fluid in the wellbore to the fluid and place it in a static underbalance. Then the coiled tubing confirms its correlation, goes back to depth to run out the delay, and the guns detonate. Following the detonation, there's inflow, they monitor the inflow, and then they pull out of the hole, and in the process, they ID the column, the distribution of fluids, including the inflow. So here are the highlights of how data were used to observe and act throughout this operation. The surface and downhole pressure data, which are the blue and orange curves that I'm showing you right here on the top left, are used to validate that a clean and reliable activation command reached the firing head. And this is crucial because a poor activation command will not reach the firing head, or rather, if it reaches the firing head might not interpret it as a valid activation command. So having this kind of data and seeing how clean that message or command makes it to the firing head minimizes the chances of misfiring, or rather coming back to surface with live guns. Now, once the guns detonate, an acoustic recording at surface picks up the bang of the detonation, and here you can see the microphone that's strapped to the well control stack, and you can see the recording of that bang. In near unison, that detonation is picked up by shock and CCL, and also in pressure and temperature transients downhole, which is what you're seeing up here on the top right. It's important that all these signals indicate detonation in unison because it provides the operator with certainty that the gun successfully fired. And then following the detonation, the inflow is monitored. Here, the downhole pressure and temperature gradually increase, and you see that you have a slight buildup in wellhead pressure until they bleed it off. If nothing else, this is validation of a successful communication with the reservoir, which is a primary objective of the run. But the data can also be used for early petrophysical modeling, so you can hand this over to your petrophysicists. Now, other firing heads have been developed, which can be activated by electrical or optical telemetries. And what I mean there is you virtually push a button at the surface, and through telemetry, you're informing the firing head downhole to detonate, right? And this greatly simplifies the workflow, and it extends it to other applications, such as plug and perf, where you can set a plug and in that same run, detonate one or multiple guns sequentially and selectively. It's in this next case study, however, which involves coiled tubing milling, that we start to see how data can be used to automate event detection. And I'll illustrate why this is an essential stepping stone, not only towards automation, but also towards unlocking reliability and efficiency. So in this campaign, each well had approximately 80 feet of cement that had to be milled. And they used the downhole tension. In this case study, they call it thrust. So you'll see that in the plots coming up. But again, tension, thrust, same thing. So they used the downhole tension, torque, and differential pressure to improve operational efficiency, focusing namely on improving the rate of penetration and reducing stalls. I'm going to refer to two wells to illustrate how the operator experience can drastically change the outcome of the coiled tubing milling job. So in well A, the operator was able to reduce stall rates and improve rate of penetration, or from now on, I'll refer to it as ROP, as compared to a previous campaign where they had no downhole data. And that's good. However, despite having downhole thrust and torque and differential pressures, the coiled tubing operator still experienced quite a few stalls. I'd like to call attention to the fact that it's unclear by looking at the data whether there was much method to how they were milling. So for instance, by just looking at it, I can't tell you where they're taking bites and where they're sweeping to clean the well bore, right? These are standard steps of a milling operation. You take a bite, you mill some of the cement, and then you perform a clean out sweep to get those cuttings to surface. But we can't tell when or how that's happening by looking at this data, at least not with much ease, with ease. Now we're going to look at the next well from that campaign, which again had 80 feet of cement that had to be milled, and they had access to the same downhole data. But just from a distance, you can already see that the data in well B has pattern and organization, and this already implies some level of method. So in well B, the case study shows that stalls were eliminated. ROP compared to well A had doubled. And we start to see method and organization. And again, what I mean here is that by just looking at it, I can tell how the coiled tubing operator took 4 bites, each followed by a clean out sweep. And to unlock this method and efficiency, the case study does acknowledge that the coiled tubing operator had climbed the learning curve and built competency with respect to piloting the milling operation based on the downhole data. So by extension, the low light here is that this level of success is highly dependent on operator experience. And therefore, it's not necessarily repeatable because what I may be considering to be sufficient thrust, torque, or differential pressure for milling may differ from another coiled tubing operator's experience and judgment. And likewise, I might have a very different approach or sensitivity to avoiding and detecting stalls than the next person. Now, for instance, here you see a plot of circulating pressure against time in the x-axis. And the circulating pressure, when the mill bit is off of the cement plug, so we're off plug, and we've established our pump rate and our stable circulating pressure, and it's more or less 3,700 PSI, a little bit shy of 3,700 PSI. And as I start to run in hole with my mill bit rotating and my downhole motor powered up, is that I'm going to start milling when the mill bit engages the cement, and I expect the circulating pressure to start increasing. So as a coiled tubing operator, I would ask myself, as I see that circulating pressure increase, when did I start milling? And I'm asking as well everyone on the call, just think to yourself, okay, I see the circulating pressure increase. Do I think that the milling starts at point A, B, C, somewhere in between those three, or maybe after C? I think we would all agree that point A, probably not. In fact, it kind of decreased the circulating pressure, but maybe point B or point C, or but we might have a debate about where did we actually start milling, and it's quite subjective. The case study developed an algorithm to detect events in a way that eliminates that subjectivity and variability and replaces it with a consistent and statistical method. And per that algorithm, milling begins somewhere between points B and C, and you can see that here with a green arrow. So that's where that intersects. Now, in the case study, they went on to implement the event detection algorithm to multiple channels. So here you can see from top to bottom, we have downhole thrust, downhole torque, and downhole differential pressure. I didn't define differential pressure before, but differential pressure, you have a pressure gauge inside of the flow path of the coiled tubing at the BHA, at the bottom hole assembly, right above the mill bit, right above the power section. Or the downhole motor. And then you also have a pressure sensor right outside of the BHA. So the difference of those two is your differential pressure, right? Downhole. Then we have at the surface circulating pressure and coiled tubing weights, surface measurements. And then here you have the mill bit depth. So this is on the y-axis here, this is just depth, and we're going to see the mill bit start moving down. And this is the time log of these 5 different measurements. And I'm going to press play, and you're going to see how this automated event detection algorithm is going to detect start milling, active milling, stall warning, and then Finally, a stall. So you can see, oh, I kind of got stuck. I think my animation, I must have clicked wrong. Let's click one more time. Okay, there we go. So now we got the full playback again, and then these indicators that I wanted them to show up. So you can see with these indicators where the start milling, active milling, the stall warning, and the stall happen in terms of depth, right? And I think that's interesting to look at. But I'm going to focus on the time domain data right now. So here the algorithm detected start milling from an off-target position. Then they entered into active milling, and then they stalled. Now the case study shows that they could detect events up to 149 seconds earlier using downhole data than with surface data alone. That's kind of an expected result, that you would have a latency. But what's really interesting from this case is that they learned that there's a 7-second window between the early warning of a potential stall, so these dotted lines here, in downhole torque and downhole differential pressure, and the actual stall, which is the solid vertical line here in torque and here in differential pressure. And they coined this as the stall anticipation window. But given the statistical nature of this event detection and the brief time that there is to react, in this case, the 7 seconds, automating the event detection is indispensable to unlocking stall anticipation and avoidance. So again, here we start to get a taste for all the good things to come with automating event detection. Excuse me. First, it eliminates the human subjectivity of identifying an event. Second, the downhole data eliminates significant event detection latencies. Third, we gain access to the stall anticipation window, which may help us eliminate stalls altogether. And finally, we can start to really push thrust and torque to maximize rate of penetration without introducing stalls. By automating event detection, we're automating insight extraction from the measurements. And this helps close the loop between the initial plan and the actual real-time measurements, and allows us to think about execution advisors which provide our coiled tubing operator with recommendations based on actual conditions. The earliest execution advisors appeared in the literature around the early 2010s, and it's interesting to see how they evolve. In this first example, the case study uses real-time pressure to estimate downhole conditions and assist in underbalance cleanouts. And I can tell you from personal experience in my previous role, that was in the digital realm, that this is still a very important advisor to work on. I'm not going to say this one in particular from that case study, but the idea of an underbalanced advisor is going to be incredibly important moving forward, or increasingly important as matures continue to produce in depleted conditions, and you must intervene them in underbalanced conditions. In this next example, we have a stuck pipe prevention advisor that looks at annular velocity, solids concentration, and coiled tubing drag to assess the risk of stuck pipe. Now, what's interesting about this prevention advisor, stuck pipe prevention advisor, is that it comes up during a time when there was an uptick in stuck pipe incidents. And this obviously created a lot of concern with the operators, because they see that they run coiled tubing, and that it's all too common and unacceptably common that the pipe was becoming stuck, which you can imagine is a fairly commercially prohibitive thing to happen. It's a very serious incident. So this advisor comes up during that time in an attempt to mitigate and prevent, rather not mitigate, but prevent stuck pipe situations. Then we fast forward to 2017, where we start seeing examples of greater data being aggregated in a single advisor. And this one, we can see alarms if the coiled tubing operator is cycling over very highly fatigued pipe. And we also see alarms if we're approaching the tensile and snubbing limits, right? So if you get very close to the yield point of the cold tubing pipe, whether it's in the tensile mode or in the snubbing mode, in the compressive mode, you want to make sure you don't exceed that because you could have catastrophic failure of the pipe. Now, what's interesting about the why behind this advisor is that it was developed in part to address gaps in competency. It was an advisor that came up shortly after a downturn where they lost a lot of talented people in the field, due to headcount attrition. It's also one of the first case studies to propose a roadmap from an advisor to automation. So it's very forward thinking. This last case study is an example of a milling advisor which integrates the tubing forces model and real-time cold tubing weight to provide the operator with a real-time estimate of the weight on bit. So that weight on bit gauge that you see here, that's not an actual measurement from a downhole tool, but rather it's the aggregation of a model, of a physics model or a tubing forces model, and the coiled tubing weight that is being read in real time from the load cell and the injector head in order to project or estimate what that weight on bit might be. We also see this feed rate gauge. So what feed rate refers to here is, should you go faster or slower? Should you run in a hole at a greater speed or at a lesser speed? If you go too fast, you're going to eventually have a stall. You don't want to do that because then that's non-productive time while you reset from the stall. Plus, stalls are not good for the integrity of your downhole motor and your mill bit. But if you're running in a hole too slowly, then you have suboptimal rate of penetration, and you could afford potentially to run in hole a little bit faster and get greater ROP without incurring that stall. So as you can tell, the themes of these advisors is that ultimately we want to make operations safer and more efficient. Now, execution advisors may be an end goal for some service providers because the next step, that of automation, may not be technically or commercially viable for everyone. That said, execution advisors are not a compromise. They are necessary precursors to automation, where instead of having the coiled tubing operator act based on the advisor's feedback, we interface the advisor directly with the asset so that it can take the control. It's a straightforward transition. In my slide, it's just I changed one icon to the other, right? But it's definitely not as simple in practice. Just consider that it wasn't until last year that we had the first successful automated coiled tubing conveyance ever. Here, what you see on the slide is an automatically generated conveyance plan on this side. An automated monitoring of the coiled tubing weight here with alarms. There's soft alarms and hard alarms, and an automated conveyance, including the pull tests. Now, one of the efficiencies that they unlocked with was safely pushing the boundaries of conveyance here. So whereas in this location, they typically were limiting themselves to conveyance between -20 and 20 meters per minute, with the automated conveyance, they pushed their envelope to -25 to +25 meters per minute. And you can see that they were operating at those limits for quite a bit of the operation. Nonetheless, this level of automation is still just one of the pieces to the puzzle that is a fully autonomous intervention. This endeavor requires a sizable amount of work before we can reach the finish line. To recap, the data journey, which has spanned almost 3 decades, can be seen as the outcome of 3 stages, which I've proposed to be observe, act, and automate. And the sequence is no surprise because we had to learn how to crawl before we could walk and how to walk before we could run. And now we are approaching the finish line, which as service providers and operators, we should all be very excited about because we will advance from automating singular tasks, such as the conveyance, to orchestrating an entire operation. and in the process will unlock a lot of value. First, we expect unprecedented consistency, safety, and predictability in the operation, and that means a safer operation for our people and our assets. With consistency and repeatability, we can start to chisel away at the inefficiencies of our execution. And this is, let me connect it back to the example of milling. When you have organized data, I mean, that's just a small part of the bigger picture here, but the consistency and repeatability in data gives you a much more obvious picture of where you can chisel away at the inefficiencies, where there are things that you can improve. And finally, with the advisors and automation, we can simplify the complexity of running the job, which means more opportunities for multi-skilling, the potential for remote operations, and reducing the number of people required for the job. Now, as we approach the finish line, we need to be cognizant of what the last mile holds for us. So what can we expect? Let's say that as an industry, we're starting to build maturity as far as automating the injector head, and we see it as a case in point with the automated conveyance case study from last year. And we've already bridged many of the important gaps related to well site connectivity, which is a much needed feature for automation and especially for remote operations later on. We still need to invest more time and resources into measuring and aggregating data and automating based on downhole tools and our fluid returns. So ongoing activities are attempting to close both of these loops, which will be critical to going beyond conveyance and automating service delivery. And where I believe that we are still crawling, if I may use similar language to the first you crawl, then you walk, then you run, is the automation concerned with the integration of fluid pumps and enabling automatic spooling of the coiled tubing. So integration of pumping will require updating pump fleet to systems that can be remote actuated, and that's not standard in your conventional pumps nowadays. And spooling of coiled tubing, for anyone who hasn't had the pleasure of sitting at the cabin and spooling coiled tubing, is pretty tricky. And the reason for that is that coiled tubing is fairly rigid and has residual bend. So automating that motion of the spooling action when you're pulling out of hole is a very tricky task, especially in the context of automating it. I'd like to conclude with 4 W's and 1 H. The W's, what? To begin, which is that we're ready to take leaps in efficiency and safety if we start leveraging execution advisors and automation. And if we push in the last mile of this journey, we will see autonomous coiled tubing operations. How we get there is to focus on the aspects of the operation that we're still crawling and walking and ensuring that we innovate in those spaces. And before we get ahead of ourselves, we need to keep pushing for data-rich operations. At the beginning of the presentation, I mentioned that today only about 20% of those operations have access to the downhole data. We must continue to grow that number. It's difficult to predict when we will cross the finish line. We should be hungry, we should be ambitious, and I propose that by 2030, we will have recorded our first fully autonomous coiled tubing operation, where conveyance, downhole tool activation, and fluid delivery are all automated. The why comes back to the value that we're going to unlock. First, we expect to see consistency and predictability, which will invite safety and efficiency. Advisors and automation will allow our crew to focus on other tasks, which will open the door to multi-skilling. And with adequate connectivity, will enable remote operations. And finally, the who, the operators and service companies alike. Both will benefit from these advancements. But I have to stress that this innovation, this journey will have to be driven by a participation and vested interest from both. With that, I'd like to thank you for your time and attention.